Hi everyone, welcome to the first tutorial. So lecture 1 was on the fluid properties, so I hope you've all read this PDF in here. What I'm going to be going through today is the fluid properties tutorial. So I hope you've read through all of these notes here and you've got some good information additional to what we went through in the lecture. And now we're going to come through and do this tutorial in here. So let's go through. So question 1, match the following terms with their appropriate symbols and units. So obviously these here, a lot of them, I guess all of them are incorrect, so we've just got to rearrange. So mass density is actually in kilograms per meter cubed. Our weight density is in newtons per meter cubed. Cool. Our relative density has no unit. Alright, remember this is row by row. Our kinematic viscosity is in meters squared per second. Our bulk modulus is in newtons per meter squared. And our surface tension is obviously lucky last. Alright, so that's the order of them. I know it's a bit messy, but hopefully you've been able to follow that. Any confusions, just hit me up in class. Now these ones here, so our mass density is our rho, and our nu is our kinematic viscosity. Cool. Alright, now let's move down. So question 2, oil with a relative density of 0.8 would have a mass density of 800 kilograms per meter cubed. Remember what we're doing is it's relative to water. So we're basically multiplying this by 1000, gets us this, so this is true. The symbol for kinematic viscosity is the Greek letter mu, true or false. This is false. Kinematic viscosity is nu. Alright. I'm going to move down this. Oh. The viscosity of a fluid increases or decreases with temperature, so it decreases. Alright, as we heat up honey, it becomes a lot more easier to move around, so the viscosity decreases. The weight density of air increases or decreases with an increase in temperature. It decreases. As the pressure applied to the water increases, its boiling point increases or decreases. Alright, this here increases. As it says in the notes, as we go up a hill, or up a mountain, sorry, if we have a higher pressure around the water, it's a higher boiling point. Just look at that chart in the appendix and you'll be able to find where this is sitting. So the kinematic viscosity is the ratio of dynamic viscosity to the relative density. Alright, this is false. This here is the mass density. Capillary action is caused by surface excess or high tension. Alright, it is caused by surface tension. The centistoke is the unit of compressibility, kinematic viscosity, or vapor pressure. Alright, it is kinematic viscosity. The relative density of a fluid is relative to the water at 0 degrees. So this is actually false. Alright, it's at 4 degrees, but it's close enough. Alright, this is just one of those wordy questions to look out for. Capillary action will cause a positive or negative error when measuring the height of the column of mercury in a glass tube. So it causes a negative error. Alright. Let's keep going down a little bit. So atmospheric pressure could be stated as 101.3 HPA. True or false? Well, that there is false. Alright, that should be in kPa. Alright, so 101.3 kPa or 1013 HPA. Pressure gauge reads negative 25 kPa. The surrounding atmospheric pressure is 101 kPa absolute. What is the gauge pressure reading in absolute terms? So all I'm going to do here is 101 subtract 25. So what this gets me is 76 kPa. Cool. For the gauge pressure in question 13, what is the value of its vacuum? Alright, so looking up here, the vacuum is 25 kPa. Sorry, my laptop's not finding this the easiest to write on. Cool, 25 kPa. The temperature in a boiler is measured as 330 degrees Celsius. What is the absolute temperature? So this is going through kelvins. Alright, so hopefully you've read your notes. You can go through this, so you get 603. 603, and that is measured in kelvins. Okay. So this is where we start going through our formula. Alright. I'm going to leave these for you guys to do, these 5. And I'm going to jump straight down. This is plug and play of the formulas, guys, that we went through last week. Look at the examples that we did. Alright. Let's come down straight away. I'm going to start working on these ones here. So I'll start with 1.1. Alright. Make sure you're reading through this. I'll go straight into the numbers. Let's come here. So going by that initial question, actually let's read about here. Sorry. So we half fill a cylinder, like a cylinder. Got a diameter of 200, a length of 1500. The weight of the liquid is 223 newtons. So these are just picking out the key information. This here is a key that it's half full. Alright. So I'll come to whiteboard, draw straight away. So doing question 1.1. First thing I'm going to calculate is, obviously I know the weight is 223 newtons. I'm going to work out the volume straight away. So the volume of my cylinder is pi d squared all over 4 times by h. It's pi times 0.2 squared all over 4 times, remember it's half full, so it's h on 2. So instead of being 1.5, it will be 0.75. Punch that into your calculator, you're going to get 0.02356 meters cubed. That's our volume. Alright, now I've got this. I'm also going to work with this one here, rearranging some formula. I know W equals mg. I know W, I know G. I can work out the mass. So 223 newtons is equal to 9.81 times the mass. Rearrange, so bring this over, and now M is 223 divided by 9.81, and that equals 22.73 kilograms. That's our mass. Now, I hope you all remember the formula, that rho is equal to the mass over the volume. Alright, so what I'm going to get from here is just plug these straight in. So 22.73 all over the volume over here, 0.0356. and that is going to give me a density of 965 kilograms per meter cubed. Make sure you're writing your units every time. Alright, if you don't write your units, I'm going to dock marks from your assessments. The other thing that we need to find out is my relative density, which, if you remember, is a rho of the substance all over rho of water. Alright, so this is equal to 965. The rho of water is 1,000, roughly. So I get 0.965 my RD. That's the final answer here. It's the final answer there. So how do we go? 965 kilograms per meter cubed, and there's my relative density. Awesome. Let's undo all of this. Okay, let's use the eraser then. So next question, 1.2. Gas of a specific volume, 0.6 meters cubed per kilogram, is in a cylinder. Got the diameter, got the length, determine the mass of the gas in the vessel. Then we're going to add a bit more gas into it, and now check the specific volume and the density. Obviously, these are the answers here, but let's go through and let's calculate it. Alright, so the formula for specific volume, so V, sorry. That is equal to the volume over the mass, which is equal to 1 on rho. Now we're given this here. The specific volume is 0.6. So what are we going to do first? Well, let's calculate our volume, which is quite simple again. Pi by d squared to 0.4 squared all over 4 times by the height, which is 1.6. That's going to give me 0.201 meters cubed. So volume of the cylinder. So I've got the volume, which is this here. Under this, I can work out the mass. Alright, so mass is equal to that down. So volume over the specific volume. So I have 0.201 all over 0.6. Which means I get a mass of 0.335 kilograms. So look, cool, 335 kilograms. Beautiful. Alright, so the next thing that I'm trying to work out, coming back here. So I've done this now. So let's add in some extra weight and let's find the new specific volume and the density. Cool. So that's part 1 done. So now the new specific volume, if I add in, is going to be, so I'm adding in the 0.5. Alright, so I had this before. I've got my mass, which is here. 0.335, 0.5. So this here comes from the question, which is quite simply 0.241 meters cubed per kilogram. Now work out the density. So density, or rho, is equal to 1 on this one, which is equal to 4.15 kilograms per meter cubed. So this one here and this one here. Okay. Now let's do 1.3. So seawater with relative density, we've got a depth, we've got another cylinder here, so we've got another 400 ml diameter. Determine the force on the plate, hence the pressure exerted by the seawater. So as soon as we see force, alright, F equals ma, or W equals mg. And once we've got pressure, it is P is F on A, so the force by area. So what do we know? Well, my RD is equal to 1.03. Alright, the next thing that I know is RD is the rho of the substance all over rho of water. This here is equal to 1000. So therefore, my rho of my substance is equal to 1030. Alright. That's in kilograms per meter cubed. That's my density. Back to the volume. So again, pi d squared by 0.4 squared all over 4 times 2.5. Okay, diameter and the depth. This is equal to 0.314 meters cubed. So that's the volume. Okay, we come back to our initial formula. So rho is equal to mass on volume. So therefore, my mass is equal to rho times the volume, which is equal to rho volume, so 1030, 0.314, which is going to give me 323.58 kilograms. That's our mass. Now, to convert mass to a force, remember I'm looking for the force, so I need W is equal to mass times gravity. This here is the force. So I get 323.58 times 9.81, which is gravity. That there is going to give me 3174.36 newtons, which is close enough to 3.17 kilonewtons. Going back to our SI units. I always bring it back to kilonewtons if possible. That's our force. So now what I need to do is I need to find my pressure, which is my force by my area. Now the area is simply this component in here. So what I get here is I get 3.17 by 10 to the 3. That's just converting it back to newtons, all over the area, pi by 0.4 squared on 4. That gives me 25.3 kilopascals kPa. That's the pressure. So that's what we have here. 3.17 kilonewtons is the force on the plate. 25.3 kPa is the pressure on that plate. Let's clean this one up. Cool. So now we're looking at 1.4. So just so you guys are aware, I'm only going to do to 1.6. I will leave 1.7, 1.8 for you to do, as well as these 16 to 21. Alright, sorry if you're bored, but we'll keep going. 2 more to go. 1.4, so a piston of diameter 15 millimeters with a length of 300 millimeters. It's placed in a cylinder and closed at the bottom end. Determine the pressure of the enclosed air when the piston comes to a rest. So to stop that piston, how much air do I need? What's the pressure of that air? Assume no friction or leakage loss. Cool, make it simpler. Density of steel is 7.8. Alright, this is the pressure that we need in there. It's 23 kPa. Okay. So, how are we going to tackle this? Well, I can start with my density is the mass by volume. Coming back to these initial formulas, I know that my RD 7.8. If I convert this again, so times this by 1,000 to get my density here, because RD rho of the substance all over rho of water. So therefore, if I rearrange to bring this to here, gets me the density. So my density of my steel, 7,800 kilograms per meter cubed. So I've got this. Now I need to get one of these two. Let's go with volume. So my volume, pi by d squared. So d in this case is 50 millimeters. So 0.05 squared over 4. But times it by the height of the piston, or the length of the piston, which is 300. Converting these back to meters. What that gives me is 5.89 by 10 to the negative 4 meters cubed. That's my volume. So now I come back to this formula here, where my mass is equal to my density times my volume. Gives me 7,800 times by this one here, 5.89 by 10 to the negative 4, which is going to give me, sorry, it's a bit shocking. Let's fix that up. OCD. So 8, 9, 4. So this here equals, let's punch it into the calculator. We get the weight of that piston, or the mass of that piston, being 4.59 kilograms. Awesome. Let's convert it now to a force, because we have to get pressure. When we hear pressure or we hear force, we always have to convert it. So W, which is a weight in force, mg, equals to the mass times gravity, which gives us 45 kilonewtons. That's our force. Now my pressure is my force by my area, which is equal to 45.07, 10 to the 3, converts it back to newtons, by my area, which is this component here again, area of the circle. And this here, once you punch them in, gives me 23 kPa. Alright, so that solves this one here. It's nothing too difficult, but that's what we're looking at. Some of the trapped air is released, so looking at 1.5 now. So what's happening here is basically flipping it upside down. So determine the gauge and absolute pressure of the trapped air. Okay, so let's try to explain this one. So what's happening initially is in our cylinder, we have some kind of piston sitting in here, pressurizing the air. We're now flipping this around upside down. So what it's going to do is create suction on this side. So effectively, we get a vacuum of 23 kPa. We get a vacuum of negative 23 kPa. That's our initial value. All right, once we flip it around, the piston wants to fall the other direction. Sorry, I'll just redraw that. So this solid piston in here, if I flip this around upside down, this will tend to fall the other direction, which causes suction. So I get a vacuum sitting in there. Alright, so the vacuum is simply this going the other direction. Now the next part of 1.5 is the absolute pressure. So P absolute, which is equal to P of the atmosphere plus the gauge pressure. Now we know this here is our negative 23 kPa, so flipping it upside down. We know this here is 101.3 kPa. So simply, the absolute pressure is equal to 101.3, take 23, which equals 78.3 kPa. Alright, so it's just more of a question to get your head around and kind of think through things, as opposed to a very calculation-based question. So lucky last, the last thing you have to listen to me whinge on about. Let's go 1.6. So a steel tank, we've got the weight of the tank, which means it's additional. We get the dimensions of the base. We've got a different type of material in here. We've got kerosene, so it's got a relative density of 0.8. We've got the depth of it, so I can work out the volume using these three numbers. The tank is supported by 4 pads, and the load is equally distributed. Determine the force on each pad and the fluid pressure on the base of the tank. So what have I got here? Well, I've got a tank sitting somewhere like that. It's not a very good drawing, it's good enough. And I have a water level or a kerosene level here. This here is a notation for water or for like a liquid. Diagrams will help through this course. So here's 2.5 meters. Here to here was 3.5 meters. Here was the 1.2 meters. Alright. So what have I got? What do I know straight away? Well, the RD of my kerosene is 0.8, and I have a weight of the tank, so my W tank is 4 kilonewtons. Heavy tank. Alright, so if this is my RD, I know that my rho is 800 kilograms per meter cubed, timesing it by 1,000, the density of water. I can now work out my volume, which is simply these three dimensions multiplied, base by width by height of the fluid, 2.5, which is 10.5 meters cubed. We come back to our initial formula as always, so rho is equal to m on v. So my mass is equal to rho times v, which is 800 by 10.5, which equals 8,400 kilograms, or 8.4 ton. That is the weight of the mass of the kerosene through here. Now the weight, alright, remember bring it to a force, so the weight is the mass times gravity, this times gravity, which is 8,400 by 9.81, which equals 82,404 newtons, or 82.404 kilonewtons. Once I've worked these out, this is the weight due to the kerosene. So I want to get the force in the supporting pads. So my force in my pads is 82.404 plus the weight of the tank divided by the amount of supports that I have. I've got 4 pads, so I end up with 21.6 kilonewtons. That's per pad. Now if I want the pressure, force by area. Now the pressure that they're asking, so we've calculated the force on each pad, the fluid pressure on the base of the tank. Alright, so what we need to do is the pressure due to the fluid is this. So this could be WF. So that is 82.404 all over 3.5 by 1.2. Gets me the area of the base through here. That there is equal to 19.6 kPa, and that is the pressure acting on the base of that tank. So that's how we tackle all of these ones. Exactly the same and similar steps to go through all of these. We will go through these two in class on Tuesday, so please make sure you've done it before then. Alright, thanks everyone, hope it was helpful. I'll see you all in class.